Right now, as you're watching this video, our sun just unleashed something incredibly powerful. On December 4, a massive M6. Zero solar flare erupted from its surface. And here's the shocking part, it came from a sunspot that doesn't even exist. NASA satellites captured images in real time, and scientists are scrambling to figure out if this monster is headed straight for Earth. The sun erupted again. Just hours later, on December 4, a newly formed sunspot region, known as AR4300, unleashed a powerful M6. Zero solar flare. It was one of the most significant eruptions from a completely new active region directed at Earth this solar cycle. NASA's Solar Dynamics Observatory captured the flare in real time, recording intense ultraviolet radiation emanating from the sun's southeastern limb. The U.S. Air Force's Space Weather Agency also detected a Type 2 solar radio burst at the exact moment of the flare, indicating a shock wave traveling through the sun's corona. This typically signals that a coronal mass ejection has been launched into space. The NOAA Space Weather Prediction Center is currently analyzing coronagraph images to determine the speed, direction, and likelihood of the CME impacting Earth. This phenomenon is ongoing. What makes this flare particularly remarkable is its mysterious origin. The sunspot region AR4300 was barely visible until December 2, but just 48 hours later, it suddenly produced an M6, 0 CME. This sudden awakening raises questions about how many other active regions are quietly storing up energy before they burst forth. NOAA is closely monitoring AR4300 as it moves toward the central disk, a position that could significantly increase the impact of flares on Earth, with solar cycle 25 showing signs of instability. The appearance of AR4300 underscores the possibility of a more volatile period ahead. Just a few days ago, another X1. 9 flare was also detected from another region, showing an unusual level of excitement from the sun. The M6. 0 event on December 4, clearly recorded by the GOES satellite, carried 60% of the energy of an X1. 0 enough to cause disturbances in near-Earth space. At the same time, the U.S. Air Force detected a Type 2 radio burst, an early sign of a shock wave, and a CME in the making. AR4300, currently located at S20E45, is gradually rotating into a more direct alignment with Earth. Any eruption from this region over the next 5-7 days has the potential to have a direct impact. Analysis of HMI data on SDO shows a complex magnetic field structure, a feature often associated with powerful eruptions. However, coronagraph data from SOHO and stereo are needed to accurately determine the speed and direction of the CME. The appearance and intense activity of AR4300 underscores the limits of space weather forecasting. Each active region sees only about half of the sun's rotation, leaving the remaining 14 days as a shadow where structures can grow unnoticed. This explains why powerful flares often appear shortly after an active region rotates forward. After the December 4 event, debate about the accuracy of the forecast flared up on social media, but experts insisted that the unpredictability of the sun lies not in model errors, but in the chaotic magnetic dynamics of the star itself. The fact that AR4300 flared so strongly just 48 hours after its appearance was not a systematic anomaly, but a testament to the complexity and mystery of the magnetic forces at work deep inside the sun. NOAA's Space Weather Prediction Center issues daily forecasts based on the current characteristics of solar active regions, estimating the probability of C-, M, and X-class flares over the next 24 hours and 3 days. These forecasts are based on magnetic field classification, eruption histories of similar configurations, and recent activity trends. By December 3, prior to the M6.0 event, forecasters may have raised the overall probability of M-class activity due to the presence of multiple active regions. But with only 1 day of data, it was nearly impossible to predict AR 4300's individual behavior. The controversy surrounding this event once again exposed the difficulty of communicating. Space weather forecasters must balance the need for accuracy with the recognition of inherent uncertainty. Overconfidence in forecasts can lead to complacency, while underestimating risk can leave satellite systems and the aviation industry unprepared. NOAA opted for probabilistic forecasting, a straightforward approach that acknowledges the limitations of technology but still provides actionable guidance to stakeholders. The M6.0 burst from AR 4300 immediately caused a radio blackout over the illuminated part of the Earth, X-rays and ultraviolet light, which took only about 8 minutes to reach Earth. Heavily ionized the D layer of the ionosphere at altitudes of 60-90 kilometers, causing HF radio waves to be absorbed and attenuated. NOAA recorded an R2 blackout lasting 30-45 minutes, affecting aviation, maritime, and amateur radio communications. But the larger concern quickly turned to CMEs that posed a much longer-term threat than the immediate X-ray burst. If it heads toward Earth, a CME carrying billions of tons of magnetized plasma could create a geomagnetic storm, disrupting power grids, satellites, and navigation. The December 4 Type 2 radio burst was the first evidence of this CME. But to determine its trajectory and speed, researchers will have to wait for data from SOHO's LASCO Coronagraph and additional views from stereo. These images will help reconstruct the CME's three-dimensional trajectory, determining whether it was simply a deflected eruption or a stream of plasma headed straight for Earth as AR 4300 gradually approached its impact point. As of December 4, data are being processed to determine whether the CME was directed directly, partially, or completely away from Earth. Given AR 4300's S20E45 position, the CME's initial trajectory was likely tilted eastward, but CMEs typically expand laterally as they propagate. So even off-center eruptions can have a small impact on Earth's magnetosphere. This was the case with the X1 9 event on November 30, which produced a CME that did not hit Earth, demonstrating that each event must be analyzed individually based on its source, location, and spatial structure. The December 4 flare peaked at M6.0. as determined by the X-ray flux in the 1.8 angstrom range measured by the GOES-16 and GOES-17 satellites. An M6.0 flare corresponds to a flux of 6 times 10 to the minus 5 watts per meter squared. About 60% of the energy of an X1.0. The Solar Dynamics Observatory captured detailed images of the flare at multiple ultraviolet wavelengths. The 131 O channel revealed the 10 million degrees Celsius plasma shining brightly at the center of the explosion, while the 171 O channel revealed the cooler coronal ring structure surrounding the eruption region. These data not only confirm the intensity of the event, but also revealed the complexity of the plasma heating mechanism and magnetic activity in the AR4300 region. By analyzing images from SDO and other observing instruments, scientists can determine the magnetic field structure and the energy release mechanism behind the flare. Solar flares occur when magnetic energy accumulated in the corona is rapidly released through a process called magnetic reconnection, where opposing magnetic field lines break and recombine at lower energy configurations, converting the magnetic energy into heat, kinetic energy, and accelerated particles. Electrons and ions are propelled to near light speeds, emitting X-rays and ultraviolet light that fuel the flare. AR4300's magnetic configuration is still being evaluated. Data from December 3-4 show a dipole structure with a densely concentrated magnetic flux over a small area, a sign of a steep magnetic gradient and the potential for strong reconnection. Researchers are looking for signs of magnetic shear where field lines are twisted relative to the field state, and a new increase in magnetic flux extending up through the photosphere, features that suggest the region is accumulating energy to create larger flares. AR4300 is also evolving. Sunspot regions typically expand over several days as magnetic flux continues to rise from beneath the surface. Sunspots are essentially regions where magnetic fields are so concentrated that they inhibit thermal circulation, leaving them colder and darker than their surroundings. Within the dark regions, magnetic field strengths can exceed 3, 000 Gauss, while the quiet surface of the Sun is only a few Gauss. As more flux flows continue to rise, the active region becomes more complex and the potential for eruptions increases. The December 4th flare coincided with the Sun entering the peak activity phase of cycle 25, which began in late 2019 and is expected to peak in late 2024, mid-2025. At the peak, the number of sunspots increases dramatically and flares and CMEs become more frequent. Cycle 25 is considered to be moderate in intensity, not as weak as cycle 24, but not as explosive as cycle 19 inches. The 1,950 seconds, but individual events in any cycle can still have a big impact. The November 30X1 9 flare is a prime example. This event originated from a different active region and produced a fast CME that was off-axis and did not pose a threat to Earth. The plasma cloud spread out into space, away from the Sun-Earth line, demonstrating that not all high-energy explosions have geomagnetic consequences. The effects of space weather are always closely related to the location of the flare, the direction of the CME, and the position of Earth at the time of the event. Scientists at NOAA's Space Weather Prediction Center are currently running forecast models to estimate when any CME from AR4300 might reach Earth. These models use Coronagraph data to determine the initial speed and direction of the CME, then simulate its path as it propagates through the solar wind. The Wang-Xiargay and WSA-Enlil models are two of the standard tools, incorporating factors about the background structure of the solar wind and the interactions between multiple CMEs if they occur simultaneously. The travel time of CMEs to Earth varies widely, from 15-18 hours for ultra-fast events exceeding 0 kilometers per second, to 3-4 days for slower CMEs traveling only 300-500 kilometers per second. Based on the intensity of the December 4 flare, it is likely to be a fast CME, although confirmation will depend on coronal imaging. If the CME is partially directed towards Earth and traveling at 200 kilometers per second, as is typical of powerful events, it could reach Earth between December 6 and 8. Forecasters are focusing on two key indicators over the next few days. The first is coronagraph images from SOHO and stereo to confirm the CME and determine its trajectory. The second is real-time data from NASA's ACE spacecraft and NOAA's DSCEV-ARVR, both located at L1, which track the solar wind and provide early warning of an approaching CME. Sudden changes in plasma density, particle velocities, and especially the direction of the intergalactic magnetic field are direct indicators of an approaching CME. The danger of a CME depends largely on the direction of the magnetic field it carries. If the CME's magnetic field points south, opposite the north direction of Earth's magnetic field, a powerful reconnection process will occur, allowing solar wind energy to flood the magnetosphere and trigger a geomagnetic storm. Conversely, if the CME's magnetic field points north, the storm-causing potential is significantly reduced. NOAA uses the KP and G scales to classify geomagnetic storms, with G1 being mild and G5 being extreme. A fast frontal CME with a strong magnetic component to the south can produce a G3 or even G4 storm. Such events cause voltage fluctuations on the power grid, mistakenly triggering protective equipment, causing currents on power lines, distorting GPS signals, and pushing auroras to lower latitudes. Sometimes visible as far north as the United States, during G4 events, as AR4300 approaches its maximum impact position, all data from coronagraph instruments and solar wind tracking ships will be crucial to determining whether we are facing a passing CME or a direct impact that could trigger a significant geomagnetic storm in the coming days. These impacts are significant for satellite operators and infrastructure managers. Geomagnetic storms increase atmospheric drag on low-orbit satellites, accelerating orbital decay. Spacecraft charging events become more likely as high-energy particles penetrate satellite electronics. Communications and navigation systems suffer performance degradation. Airlines divert flights over polar regions to avoid loss of high-frequency communications and increase radiation exposure. Power grid operators implement mitigation procedures to protect transformers from geomagnetically induced currents. This is unprecedented in one sense, the rapid succession of significant solar events. The X1 9 flare on November 30, and now the new M6. 0 flare from AR4300 on December 4 show the sun's erratic behavior during its maximum phase, while multiple eruptions over several days is not unusual. The involvement of different active regions and the rapid activation of AR4300 show how volatile the current solar environment can be. Scientists are also assessing whether AR4300 could produce further eruptions. The region is still visible on the sun's disk and will continue to rotate toward its optimal position toward Earth over the next week. If the magnetic field configuration continues to evolve, especially if new flux or shear increases, the likelihood of further eruptions remains high. NOAA forecasters will update space weather predictions daily based on ongoing observations of AR4300's magnetic field structure and any signs of increased activity. The U.S. Air Force Space Weather Agency plays a key role in tracking and forecasting solar events that pose a threat to military and civilian infrastructure. Systems such as strategic satellites, military communications networks, and navigation platforms are sensitive to fluctuations in the magnetic field and radiation emitted by solar events. Therefore, the ability to detect CME activity early and accurately analyze the signs of CME activity is a key element in protecting space security. The Air Force-operated Solar Radio Telescope Network provides continuous monitoring across multiple frequency bands, particularly capable of detecting Type 2 and IV radio bursts, shock wave signatures, and CME activity. This data directly complements optical observations from NASA and NOAA spacecraft, creating a dual alert system that provides rapid confirmation of high-energy events. Coronagraph analysts are currently examining SOHO's LASCO C2 and C3 images to measure the CME's angular aperture, speed, and trajectory. Coronagraph C2 observes an area between 2, 5, and 6 solar radii, while C3 extends the field of view to 30 solar radii, allowing the CME to be tracked from its initial expansion phase into interplanetary space. The CME appears in these data as a bright, expanding structure moving outward. By measuring the position of its leading edge frame by frame, analysts calculate its speed. Comparing its position with background stars helps determine the plasma's three-dimensional trajectory. The latest analysis shows that AR 4300 is a small, sunspot-rich region with a complex magnetic field structure and is potentially active. Ground-based observatories, such as the McMath-Pierce Telescope and the National Solar Observatory's GONG network, are using space-based instruments to monitor the region's evolution in real time. The combination of ground-based and satellite observations provides scientists with an independent layer of verification, helping them better characterize AR 4300's evolution and assess the risk it may pose in the coming days. Current observations show that solar activity levels remain high compared to the relatively quiet conditions during the recent solar minimum of 2018 to 2019. During that period, days without visible sunspots were quite common. In contrast, December 2024 will see multiple solar activity regions appear simultaneously on the visible disk of the Sun. This increased activity is expected to continue through 2025 and into 2026 as solar cycle 25 approaches its maximum phase. Scientists are looking to a broader range of space weather monitoring capabilities. The solar observation fleet includes NASA's Solar Dynamics Observatory in geostationary orbit, which provides continuous high-resolution imaging. The Solar and Heliospheric Observatory at the L1 Lagrange point provides coronal and helioseismic imaging instruments. The twin stereo spacecraft, one now retired, provides off-axis imaging of the Sun. Ground-based observatories around the world contribute optical, radio, and magnetic field measurements. This network of observing platforms allows for comprehensive space weather monitoring, but there are still many shortcomings. The dark side of the Sun cannot be observed directly except through helioseismology, which provides limited information. The time between a CME launch and its arrival on Earth allows forecasters hours to days of advance warning. But accurately predicting the intensity of geomagnetic storms remains a challenge because a key parameter, the CME's magnetic field direction, cannot be measured until the plasma cloud reaches upstream monitoring spacecraft, just 30 to 60 minutes before impact with Earth. Summary: the December 4 eruption of AR 4300 highlights the dynamic nature of solar activity and the inherent challenges of space weather forecasting. The region emerged, grew, and produced a significant flare in a short period of time, limiting forecasters' ability to provide early warning. This pattern is typical of solar active regions, which can evolve rapidly and unpredictably. The question now is whether this CME will impact Earth and what the potential impacts will be. If coronagraph analysis confirms an Earth-bound trajectory, NOAA will issue a CME warning and monitor geomagnetic storms. Satellite operators will review spacecraft health management procedures. Power grid operators will prepare to mitigate geomagnetically induced power line impacts. Airlines will monitor space weather updates to inform polar flight routing decisions. Amateur radio operators and aurora watchers will prepare for possible auroral activity at high latitudes. Over the next 48 to 72 hours, as coronagraph data are fully analyzed and propagation models are refined, the space weather forecasting community will have a clear answer about the potential impact of the December 4 CME on Earth. The December 4 event demonstrates that even as forecasting tools improve, the Sun retains the ability to surprise. Active regions appear, evolve, and erupt on timescales, defying the ability to predict. Scientists continue to work to improve space weather models, expand their observational range, and improve their understanding of the physical processes that drive solar eruptions. Each major event, like the M6, zero flare from AR 4300, provides data that helps advance this effort. As of December 4, the Sun remains highly active and unpredictable. Numerous sunspot regions are present. The potential for solar flares remains high, and the possibility of additional CMEs remains, as long as complex active regions remain in the solar disk facing Earth. What's happening right now in M6, zero flare from sunspot region 4000, 300, a type 2 radio burst that suggests a possible CME, and ongoing analysis to determine the potential impact on Earth, reflecting the reality of space weather in the solar cycle. If you want to stay up to date on the latest solar events, CMEs, geomagnetic storms, and ongoing scientific analysis, be sure to subscribe so you don't miss any important developments. Leave a comment with your opinion. Is AR 4300 just the beginning of a larger chain of events in solar cycle 25?